interference on thin film. Okay, interference on thin film. Very important question topic. Very important topic. This is. Here we explain how the light interfere on thin film. Okay. So for that, here we take a plain parallel thin film. Plain parallel thin film. We take a monochromatic source. That monochromatic source falls on the glass plate or thin film. Monochromatic source falls on glass plate or thin film. Some part of the light reflected by the upper surface of the thin film. Some part of the light transmitted through the film. And again this transmitted light reflected by the lower surface of the film. These two reflected rays superimpose at a point. The intensity modified as maxima and minima. Then interference means the intensity modification as maxima intensity and minima intensity. When the intensity modified, the two light rays superimpose. Those two light rays must in coherence. When the two light rays are in coherence, then they are superimposed. The intensity changes as maxima and minima. In these two light rays which are coherence, those are two reflected rays. One light ray reflected by the upper surface, one light ray reflected by the lower surface. These two reflected light rays superimposed at a point. From that superposition point, the intensity changes. That intensity change as maxima and minima. At that maxima intensity, bright fringes are formed. Minima intensity, dark fringes are formed. At maxima, bright fringes. Minima, dark fringes. Why the intensity maxima, minima? At the two reflected rays superimpose in phase, constructive interference takes place. The intensity changes as maxima. When the two reflected light rays superimpose out of phase, destructive interference takes place. The intensity become minima. At maxima intensity, bright fringes form. At minima intensity, dark fringes form. Okay. For that, for that explanation of this interference, we take a plain glass plate. Here, see here, this is the plain glass plate. This is the monochromatic source AB. This monochromatic source incident on this film. Some part of the light reflects. This is R1 ray, and some part of the light transmitted to the thin film. And again this transmitted light ray reflected by the lower surface and emerges through upper surface. These two reflected rays, R1 ray and R2 ray, superimpose. When they are in coherence, they are superimposed. From the superposition point, the intensity changes as maxima and minima. That intensity shows like a bright fringe and a bright and dark fringe pattern. Okay. So here we take the plain glass plate having the refractive index mu and thickness, same thickness. This is the uniform film. So another way this question is the interference on uniform film. Okay. Here the angle of incidence is I, refraction angle is R. So here we find the path difference between those two reflected rays, because we obtain bright fringe and dark fringe. So we want the condition for bright fringe and dark fringe. General condition for constructive interference is path difference is equal to integral multiple of lambda, and also if any way we write the conditions, we want the path difference. So we want path difference in between these two reflected rays. So here the path difference is BC this reflected ray R1 reflected ray have the path Bn and R2 reflected ray BCCD. So these two paths here we want the difference between two paths. So path difference of the two light rays is mu into, so mu means refractive index of film. So this light transmitted light and reflected, that light ray travel in this film BC plus CD. So this is the path of this light ray R2 and mu is the refractive index, and here Bn is the path of the path in air. So we want the path difference between these two reflected rays. So here we want BC plus CD. BC plus CD. For BC, we take the triangle BCM. In triangle BCM, cos R. Here cos R is equal to CM by BC. BC is equal to T by cos R, because CM is the thickness of the film. So here T is the thickness. So we write in place of CM T. So BC is equal to T by cos R. From triangle in this triangle CDM, in the triangle CDM, cos R is equal to CM by CD. CM by CD. Cos CD is equal to T by cos R. So BC plus CD is equal in triangle BMC, tan R is equal to BM by CM. BM is equal to T tan R. Similarly, MD also, BM and MD also T tan R. So BM plus MD is equal to 2T tan R. From triangle BND, here we see here BND, sin I, this is the I, sin I is equal to BN by BD. Sin I is equal to BN by BD. BN is equal to BD sin I. BD means BM plus MD. BD means here BD means BM plus MD. T tan R plus T tan R into sin I, 2T tan R sin I. From Snell's law, we know already Snell's law, mu is equal to sin I by sin R. So sin I is equal to mu sin R. Bn is equal to 2T tan R mu sin R. Path difference. So path difference is equal to mu into BC plus CD. That means mu into 2T by cos R minus 2 mu T tan R sin R. 2 mu T cos R. We common this term 2 mu T cos R. So here 1 minus sin square R. 2 mu T by cos R into 1 minus sin square R means cos square R. So 2 mu T cos R get cancelled. So 2 mu T cos R. The point B, so this is the path difference between two reflected light rays, 2 mu T cos R. So in this diagram, the path difference, the point B reflection occurs from the denser medium. Light ray undergo an additional phase change of phi or path difference of lambda by 2. According to Stokes' theorem, the surface of the denser medium reflected on the surface of the denser medium, the light ray reflected, it makes a phase change or a phase change pi or path change lambda by 2. So here we obtain additional path difference due to the according to the Stokes theorem. So 2 mu T cos R plus lambda by 2. This is the total path difference between two light rays. Due to two reflected light rays, the path difference is 2 mu T cos R plus R minus lambda by 2. When we obtain path difference, we write the conditions for bright fringe and dark fringe. Bright fringe and dark fringe. When the path difference is equal to the integral multiple of lambda, then the light rays meet the in phase and undergo constructive interference. So, light rays interference is the two reflected light rays the two light rays interference are superimposed in phase. There exists a constructive interference. Then the intensity changes as maxima, bright fringes appear. So the condition for bright fringe is generally the path difference is 2 mu t cos r plus lambda by 2. That is the path difference. 2 mu t cos r plus lambda by 2. That path difference is equal to n lambda. Here the condition is the path difference is equal to n lambda. So 2 mu t cos r is equal to n lambda minus lambda by 2. 2 mu t cos r is 2n minus 1 lambda by 2. So that is the condition for bright fringe. So this is the condition for bright fringe. Next we go to condition for dark fringe. Dark fringe obtained when the intensity become minimum. When intensity become minimum, the two light rays superimpose out of phase. When out of phase, they light two reflected light rays superimpose out of phase, destructive interference takes place. When destructive interference takes place, the intensity become minimum. So here destructive interference takes place. That's why the intensity becomes minimum. The general condition for destructive interference is the path difference is equal to half integral multiple of lambda. So we are equating that path difference to this half integral multiple of lambda. Then we obtain 2 mu t cos r is equal to n lambda. This is the condition for dark fringes. So we write the conditions of dark and bright fringes. Okay. Depending upon the above conditions, the interference pattern consists of bright and dark fringes. See in this diagram, we obtain the intensity as brightness, darkness, brightness, darkness. Okay, this is the interference on thin film. This is very important question for 10 marks question. You remind it. Okay, thank you.